So today we're basically turning our attention from the formation of rock to the formation of soil, and those two things are joined together, and we'll explore it, and it'll make a lot of sense to you, I hope. I put this on here not because I don't want to draw attention to myself or anything like that, but I wanted to talk about the timeline. So when I was in graduate school for one of my degrees, I did my dissertation on soil fertility, and at the time, it was just starting to be a topic that a lot of scientists were starting to study. Since that time, so you can see the publishing date for this particular thing was in 2015. Well, the amount of people studying soil fertility and soil science has quadrupled since 2015, and it's not because people read and were inspired by my work. It's just because people are really getting into this as a subject. And there are more people studying soil science right now and looking at technology of soil science than were studying space and working for NASA in the 1960 decade. And the reason why is because as we look at global change, some estimates have come out that are really stark and very scary, that the amount of topsoil on planet Earth will be all consumed in a 60-year period of time. And it's because we've really disrupted this cycle of formation of soil that takes a really long time. So we're going to get into the processes of how soil is formed, and we'll be able to think about that in the back of our mind as, well, it takes a really long time for these processes to occur. So 2 learning objectives for today, really simple, really discrete. We're going to understand weathering and erosion, and we'll kind of break those terms down into their component parts, but understand how do they contribute to the movement of soil and the turnover of soil, but also just we'll spend most of our focus on the formation of soil because that's the big key. And then the next thing we'll talk about is how soil forms and talk about its characteristics, and that word characteristics in terms of soil is going to be deep. There's some must-know definition things that you have to know that come out of today's lecture. So even though this is a simple sentence, there's a lot. This has a lot in it. So let's go. Let's rock and roll here. The first thing to talk about is just a little review over what we did from rocks yesterday, but we want to think about it as its relevance for soil. So this is, I put this on here because I noticed there were a few people who missed it on the formative, and that makes sense because we didn't really talk about it that much. And I see a lot of misconceptions around this in the way that people talk about it and use the language around the formation of soil or rock. But the mineral is this naturally occurring inorganic. So what I'm talking about there is it's not carbon, hydrogen, and oxygen molecules, but it could be something like a complex aggregate of aluminum, copper, and silicone. But we're talking about these compounds and crystalline structures that make up the geological processes. So rocks are made of these minerals. Soil is made of these minerals. So we usually like to think about minerals because of that compound aggregate thing and not just think about elements because the elements, as you know, form complex compounds, and those compounds have different properties than the elements they themselves have. So minerals is the key thing to understand, and it composes rock, it composes soil as well. So rocks are, we didn't take much time to define this, but now that we're in this setting, a rock is an aggregate of all of these minerals. It could be one mineral, so we're looking at the moles or the total amount of certain compounds, but it could also be a bunch of different minerals, and it could include some of the organic material. So things that came from usually biological living organisms at one point in time. That's important because some rocks are combustible, and the combustible rocks happen to be the most functional and highest utility rocks for human society that exist on planet Earth. So that piece of the organic part is important. But a lot of mineraloids, things that we use in everyday consumer goods, that's what we're talking about when we talk about rocks. The last one here is that some rocks are composed of one mineral, and so we pay attention to that as well. this is not new. I know it's redundant, but just respecting the fact that we have a lot of movement back and forth, and there are three agents of change that really contribute to rock, and this is how we characterize rock. We don't really care about what the rocks are made out of, but we do care a lot about how they're formed, because their properties are more variable based on how they're formed than what they're made out of. So the three agents of change are weathering and erosion is kind of one category of sedimentation. And then we have pressure, and then we have heat. And from yesterday, in terms of review, which one is the most important? Heat. Heat has the most transformative impact on rocks. If we push that into the asthenosphere really deep and we turn those minerals into liquid, that's when we're really changing the rock the most. Beautiful. I really like this table right here, and I put it together. The main thing to walk out of this to know is this formation piece. So you need to be able to match the formation with the type of rock, because that's key for the characterization. But I put some other details on there just to kind of get our minds into it and wrap our heads around it. A couple things from the lab yesterday, etc. What I want you to do is look at this table, and instead of just me asking, does anybody have any questions, I want every person to think of a question, and it can be a clarifying question or just something that you're curious about, and ask your table group or a group of three of people around you, and then we'll talk about a few things together. So take a couple seconds to digest what's happening here on the table, and then figure out a question and ask some people. We had some good questions last period. While you do that, I'm going to take attendance. No questions at all? Man, one question from Cal. Cal would have the only question. Joe's got a question. We'll come back to Cal. Joe, what do you got?
So yesterday we talked about how basalt and granite differ because basalt is, I forget the word already, but like it's
extrusive.
Yeah. Granite's intrusive, but there it says that they're like made of different minerals. So
for sure. Oh, great question. So on one hand, and it says on the front side of that document a little bit about the minerals and this interaction. So what the rocks are made out of matters less than how they're formed, right? But in the case of, well, granite and basalt are both formed through the same process. So one of them is formed extrusively, meaning it was exposed to usually air or water. In the case of basalt, a lot of times that's, well, it's associated with divergent plate boundaries and things are moving apart. So you remember that new rock being formed, a lot of times that's oceanic rock that's made of basalt that's coming out. And so it cools really quickly because it's exposed to water, and it cools it down, and that contributes a little bit to the density of it. But the other piece that's interesting is that it's made out of different things. So if we look at the density of, if you had the same amount of moles of each one of these, which one would be denser? It would still be basalt because of the molecular weight. So both things are actually at play, contributing to the density of basalt. But in this case, and the density that we were considering, we were looking more about its cooling, and which one would be more dense. What's interesting about this is if we talk about extrusive rock like pumice, or that type of porous rock like lava rock that you see in people's garden, that volcanic rock is exposed to air and it dries extremely quickly. How do you know what type of rock I'm talking about? Yeah. How does it feel?
Very light.
It's super light. And why?
It's got a lot of air in it.
All that air in it, right? So in that case, it cooled really fast. It's extrusive too, but its density is really light because it had pockets of air. And so I won't ask you to navigate all of that. That gets us into, we just wanted to do it as this one exercise because it's cool to do as an investigation and it's interesting to understand. I won't ask questions about this because this is more advanced geology. As long as we understand this, that gets the surface. But those are really interesting things to explore, right? There's an interaction of density, extrusive, intrusive types of minerals. All of those are at play. Cal, what do you got for a question?
So can we make the argument that both sedimentary and metamorphic rocks come from igneous rocks?
Yeah, and if you remember in the video at the very beginning of that introduction to igneous rocks, they say, these were the original rocks, which is why they're sometimes called primary rocks. Well, because at the beginning of Earth, 4.5 billion years ago, volcanic activity was what was creating all of the rock, and the only thing that was turning over material on the lithosphere. But now we've had a lot more time, and so we have a couple more things. A really good question that came out yesterday was whenever we get down into the asthenosphere and we have that heat, that's really when we get to the igneous rock. So that's why we see those types of rocks at the plate boundaries. But metamorphic rock is when we're pushing material down, and of course we have layering and you have weight and gravity that's forming those rocks, but because of the proximity, you're on the edge of the lithosphere. So here's the surface of the Earth, and maybe really far down here is where you're closer to the asthenosphere, and so you have frictional heat because of the weight, and then you also have proximity to the asthenosphere. That's what's forming those rocks. And what I really like here is these materials are in a lot of building materials, but this is where we also find coal, right? So this type of rock, it's buried deep. You know, if we're going to mine coal, we have to dig into the earth, right? And we're digging down, and that frictional energy and that exposure to its closer proximity to the asthenosphere, that's what's forming that type of rock. So that's really key. We'll talk a lot more about coal, but when I mentioned the organic compounds, this kind of rock is combustible. Well, that matters a lot because that's powered basically everything in human society for a couple hundred years. So it ends up, that fact that there's organic material here has really mattered a lot for our existence. Okay? All right. Let's go here. So I put this on here just as like a little spacer as a reminder. As we talk about these geological processes, and aforementioned a second ago, 4.5 billion years since the beginning of Earth, and humans have come in and we've started to disrupt geological processes through mining and movement of rock to build roads and buildings and things like that. But we've interfered with the formation of soil, which also takes millions of years in a scale of time, in a much more severe way. So when we get to the human impact piece later, and we'll just kind of file this in our minds because we're basically just trying to understand the processes now, but when we get to human impact later, our impact on the soil has been far more severe than our impact on the geology. Okay, and so you can see movement of rock. It's funny. You can watch it later. It's cute, little cartoon guy. Oh, rock with the big nose. All right, you may have noticed on the lectures, I've been trying to do this for your purposes, but when it's key, that's key terminology that usually shows up again, and I want to try to shortcut in our language instead of using the full descriptions. That's why we create nouns to refer to things. So this parent material and erosion are some key things to understand. There's this typo here. This is supposed to be rock fragment, by the way. But parent material, whenever you hear the word parent material, we're talking about the rock. Why not just use the word rock? In this case, it's because we're trying to refer to something specific in the soil. So you only hear this word parent material in context of talking about soil and soil formation. So it's the rock and everything that makes up that rock. It's inorganic compounds, all the minerals, its density, what type of rock it is, metamorphic, sedimentary, or igneous. All of that matters a lot for the formation of soil. So whenever you hear parent material, think rock. This process of erosion is a big umbrella term that can speak to all types of different processes. So it's the physical removal of rock fragment. So if I have a big igneous rock in my right hand and then I act on erosion, how does it look different after erosion? What does it look like later? Smaller, right? And how do I break that down? How do I go from rock to smaller rock?
Friction.
It could be things like friction. What else?
Getting struck with something.
Getting struck with something, like if I take a hammer, right? Could have a little bit of heat, although probably less likely to occur in nature, but it could be theoretically something.
Like, or if you got sand and like wind blowing at it. So
all of these processes, that whenever we have big intact rock to smaller pieces of rock, as an umbrella term, we call that erosion. And so we can make this more specific by looking at a couple different factors. But I first want to talk about this as kind of a process here. So on the far left-hand side, we have intact parent material. And we have immature soil on the top. Over time, due to erosion forces, we're going to break that rock down into smaller fragments. Erosion, small fragments of rock. And it takes time for those processes to occur. The longer time goes, the more mature the soil becomes. And we're measuring maturity of soil by looking at these layers and these fragments of rock. So there's a relationship between time and erosion. Excellent. Let's talk about these factors that actually determine the soil properties. And what you'll see is there's a link between what we just talked about in terms of erosion. All of these factors that we'll talk about contribute to erosion. And we always want to make sure to use the right word here. So soil is the word that we'll use because of its link to the biotic factors on the planet. The word dirt refers only to the chemical attributes of the soil. So on an assessment, if you're talking about things and you're using the word dirt, that's inappropriate. We want to use the word soil, and it seems like a small nuance, but it's an important nuance because this contributes to the biotic factors much more than the dirt does. So one of those things that helps form soil, and this makes perfect sense, is what is the topography of the parent material? So if it's a really steep grade, and then we have things like wind or water or glacial activity, all of those are going to move faster because it's gravity that's moving. Water always flows to a lower point, right? So the steeper that grade, the faster these erosion forces can take place, and the quicker soil is being formed, and the more the parent material is being broken down. So that's number one. Number two is the climate. And this is a big one. Sometimes students ask, well, why do we do climate and weather before we do this earth science and geology? And the reason is because when we talk about the soil, I want to make sure that we already understand the climatological forces. So climate, if you have glaciers, in some area, you would have glaciers in one area versus a different area because of the climate that they occur in. But also the biological organisms, which I'm going to bring up the next one here, the amount of productivity and the number of organisms that are interacting in a space is driven by the climate and weather. So if it's an area that's not very hospitable, and it's a really hostile area, like at 30 degrees north or south where you find a lot of deserts, or high up on a mountain because of increased altitude, we have less biological productivity, and therefore those organisms are interacting with the soil less. Where in places where you have a lot of biological activity, like the tropical rainforest, you're both taking from the soil a lot and contributing. In this case, the rainforests have extremely poor soil quality because they're drawing the nutrients up. The productivity there is almost too high for the soil to be formed. There's no seasonal variation so that you never get material falling and decaying, and then the soil, the rest, and this time process. So some of the places with the most productive soil are in these grasslands and temperate seasonal forests. And so that makes sense. Climate and weather, the way these things interact in terms of forming soil, they're related. A lot of times we use time as a way, as I mentioned, there's a relationship between time and erosion forces, but the more time you have for these sorts of things to interact, the more the soil will be formed. And so if you look at soil and it's not very formed, and where do we start the clock is whenever the new rock is formed. So if new sedimentation occurs, we have new rock being formed. If we have igneous rock, new rock is being formed, and the amount of time that goes by, that contributes to the soil. And the last one is what it's actually made out of. So yes, it matters what the parent material is in terms of its chemical composition and the compounds, but it is only one of about 5 factors. A lot of times people think that that's probably the most important, and it's actually one of the least important. Okay? Beautiful. Questions over this? I'm going to give a second or two to make sure that you have all this written down so that before we go to the next slide, because I got a little formative thing put together here. All right, let's do it. I wanted to put this on here as an exercise. These are good questions, and they're actually tough questions. They're hard to address fully, but I also wanted to mention it and do some coaching for assessment. So in order to be successful on these types of questions, of course, a lot can be said. If you say one thing that's right and then one thing that's wrong, those two answers negate each other. So I have trouble awarding 4 points if you say one thing right and one thing wrong. What you should think of is how do I directly and concisely address this question? So for example, if you see the word describe, usually what we're talking about when I put the word describe, what I'm asking you to do is give me first this happened, this happened, this happened. And we're always looking at processes. And I'm looking for you to name key terminology or key phenomena that helps describe why this process proceeds as it does. So for answer 1 and 3, about 1 to 4 sentences is totally sufficient. 4 is a lot. 1 or 2 is excellent. Just saying, hey, it's just this, right? And if we're talking about explaining, I'm looking for you to break down the phenomena that you're observing or that I've given you context to. And so in this case, I'm not asking you to give the steps, but I'm asking you to explain what is the key scientific principle, law, or concept at play that actually causes this to occur. So we'll take about 4 minutes, and that's the same amount of time that I would give. I would give you about this amount of time to process a question, and then I explained it, but we've been talking about this. And then you would have about 4 questions to answer these types of questions. So I want to give about that amount of time so you can practice as a formative thing. You don't have to go very far to get the answer because a lot of them are on the slides and notes that you just took. We'll talk about them in a large group in a minute. I got about 1 more minute here. All right, beautiful. What do we got for number 1? What do we have for number 1? So I've got parent rock on one side and then mature soil. How do we go? Yeah.
Often the climate brings in additional nutrients which affect the soil's makeup.
So we've got additional nutrients being brought in. That would be a good partial credit because that's one factor. Yeah.
The parent rock, which is or the parent material at the bottom, is weather and moves upward, and then also plants and organisms that die are accumulated on the surface.
Beautiful. So we have, and the pictures kind of misled you a little bit, so I'm glad that you put that on there. So the parent rock is broken down through weathering processes. So, and which things would contribute to the rate at which weathering and erosion occurs? Well, topography, climate, biological organisms, the composition of the material, all that stuff that we just talked about on the previous slide. So if you name those specific things, that's the best quality full credit answer that you can give. But the piece where you said it moves up, it looks like it moves up. That's kind of the image betrayed you a little bit. It's not that it moves up, it's just that it's broken down more on the top. Because of why? Why would it be broken down more on the top? That's exposure to the weathering and erosion is. So that intact rock that was big is broken down, and it's broken down more on the top because that's the side that's closest to the forces. Does that make sense? All right, we can do number 2 and 3 kind of together actually. So how do nutrient values in soil change with age? What do you think? Yeah.
So young soil has like very few nutrients, while like mature soil has, I thought, the most, and then the older soil has less than that because the plants in it have taken away the nutrients.
So definitely more mature soil has higher nutrient value than just the parent rock. And then let's do number 3 before we do the roundup here. What about number 3? How can this happen at the same time? Yeah.
You always have biotic factors using the nutrients.
So the big key about soil, and why we're not just talking about it in terms of earth science, is soil is the link between the biology, the biotic factors, and the abiotic. So as these die and decay, we have soil being built up and nutrient values going up, and then we also have nutrient values going out because biological processes are drawing on the soil. Does this make sense? Okay, good. Nice. Good exercise there. Where did I put my mouse down? Here it is. I need to get a presentation tool thing. All right. Good. This is a definite must-know, gotta understand it sort of thing for this class. It comes up a lot. It's been on the AP exam every year that I've taught the class, and it really matters to understand. So we're going to kind of break it down, and I'm actually going to start at the bottom layer, given what we just talked through as a group. So the parent material, that bedrock layer, is slowly broken down over time into rock fragments due to erosion and weathering, those two types of processes. And as it gets broken down, the fragments become a little bit smaller. So this layer that's closest to the intact parent rock, the parent material, we call the subsoil. It's really far down, and our label for that is the C horizon. And you'll see there's an alphabetical part to this, but there's some weird letters that are thrown in as well. But C is at the bottom. C is the subsoil. It's closest to the parent rock. So some weathering and erosion has occurred. And just as Cal said, well, the particle sizes are the largest here, because they're the least exposed, so they've only been broken down a little bit. The subsoil layer above that is the B horizon. The main difference between B and C is the particle size. So in the B horizon, it's a little bit closer to the top, and so its exposure is a little higher, so the particle sizes are smaller. Now we're going to kind of take these three layers together. So on the very top of the soil is this layer called the organic layer, the O horizon. So this is where all of the interchange and exchange of nutrients with biological processes is taking place. So plants and organisms are falling down and decaying, and decomposers like earthworms are breaking it down, and insects and whatever. We call that the O horizon. Sometimes you also call that layer humus if you've ever been around any of this before. So this area is really rich. There's a lot of carbon. There's a lot of key nutrients there. Right below that is the topsoil. If you know anything about gardening or have studied any of this before, again, you've probably heard this. The topsoil has a lot of nutrients in it as well, but it's not the organic stuff. You don't actually find root material or dead leaves or things like you have in the organic layer. It's been broken down more than that. So the particle size here is the smallest because it's the highest level of exposure to the erosion and weathering forces. The largest down here at C, the smallest up here at A, and then we just have a mat of organic layer above that. And then you have this kind of oddity in between the A layer and the B layer, and we call this the zone of leaching. Not all soil profiles have this zone of leaching. A lot of soils do. It's usually the ones that are the most productive. And you see under this it says the zone of leaching of metals and nutrients occurs in soils either here or there. And what I put in here is it's the movement of material. So we have some exchange happening between A and B. And if you have metals or metalloids that are water soluble, when rain or other forms of water fall on the soil and permeate down, it dissolves those metals or metalloids, anything that's water soluble, and they keep going down through the soil. It can only move in one direction, so it happens due to gravity, and that water takes it down through the E layer, and then you get an accumulation of the metals here. So in areas where you have a really dense E layer, or you have a lot of water soluble metals in the A layer, the B layer is semi-toxic. So the healthiest soils have a really thick organic layer and a really thick topsoil layer. The smaller those layers are in the profile, the worse the quality of soil is, and the harder it's going to be for nutrient exchange and biological processes. If the B layer is really thick and you have a pretty dense E layer, your soil is almost toxic. You could have a lot of cations, you could have a lot of metals here. It's not a good situation.
So, which one's good?
They're all good, but you want to have a really thick O and A layer is the healthiest. You'll notice in this picture there aren't very many roots that penetrate all the way down to the B layer. But if you have really productive soil profile, the O layer and the A layer is really thick. We're gonna collect some soil samples from around campus, so you'll get some experience looking at this and identifying this. You'll see our soil on campus is awful, which makes sense. It's highly developed area, you know. Okay, excellent. Feel good about this? This is a must know. Got to know it. Got to know the layers of the soil. I kind of already talked through this. So I put this graphic on here just to show this process a little bit more. And we've zoomed in a little bit. So weathering and erosion occurs. The bedrock is the largest particle size. And then these layers get smaller and smaller in terms of particle size as you go from the parent material or bedrock and you have time playing. I'm going to skip this, even though I want to give it to you on the slides, and there's another formative exercise that goes along with it to take a couple seconds and a really good video about soil. But I want to move on to this just so that we can get into it a little bit. So I'm going to give you this. Thank you. don't know why the printer like smudged it all up. Sorry, I need to print off another one. I printed the wrong number because I was, share. The soil texture triangle. So in order to categorize our soil, we use it by looking at the particle size, because particle size really drives health of the soil, and certain plants and biological processes are only found in certain types of soil. And the weathering and the erosion is how these composition layers are produced. So as you look at this, we have sand is the largest particle size, silt is in the middle, and clay is super small, compact, and dense particle size. Which one would be on top? We've got sand, silt, or clay. Which one would be on top? I heard both answers. So somebody who said sand, why do you think sand?
Smallest.
It's biggest.
Oh, it's
Sand is the biggest.
the opposite of
Okay. Spence, you said clay. Why clay?
Because it's the smallest.
The smallest, and help me make the link. Why would the smallest be on top?
Should be most weathered the most.
Weathered the most, highest rate of exposure, right?
Right.
So the same thing that's true for looking at our soil and looking at the horizon layers that we've been talking about is true for this. So as you look at this graphic, and I know it's kind of a tricky one, we're trying to find the point at which the three layers intersect. So in terms of understanding it, it tells us how the soil in terms of its texture and coarseness is. And so when you look at this, I didn't write down an example, so I'll just make one up. Say we have 40% sand, 20% silt, and what does that make us? 40% clay. You have these number lines going across, and the easiest way to do it is in a clockwise fashion. So if I take my number line here is 0 for clay, and I'm going to go up until I get to 40. And it's always the lines that, as you look at it, moves from the far right to the upper left. So this is my line for clay. Then I'm going to go to my silt. Here's 0, here's 100. I'm going to go to 20, and I'm going to move this line. You'll notice they already intersect, which makes sense, but just to double check, my sand line here is 0, and so I go up to 40, and then I move in this line. So the point where all three of these intersect is right here, and so the type of soil that I have is clay loam. Okay? We're going to deal with this a little bit in class, so I just wanted to expose that to you, and you can work through the worksheet as just a practice exercise. I'm not going to collect it, but just to develop a little confidence with the tool. What do you guys want to do? You want to work on the worksheet, or you want to do the other formative that I had on the slide before? Which do you like? We've got 3 more minutes left.
The worksheet's probably easiest.
They're both easy. They're both good. Well, you stop the recording then, since if we're gonna do the worksheet, and we can just kind of round out the time.